Good day, everyone. I am by name Mr. Samuel Eindero, and I will be taking you physics. Our topic still remains calorimetry 1, and I expect that by now you've already downloaded the slide which explain all the theoretical aspects, aspect of this topic that you need to know. We are here to just solve the questions in that slide. The examples in that slide. That is from example 1.1 to example 1.3. Now, example 1.1 A. Example 1.1 A. How much heat is required to raise the temperature of 250 milliliter of water from 20 degrees Celsius to 35 degrees Celsius? We are given the volume of water to be equal to 250 milliliter, which is same as what? 250 centimeter cube of water, because 1 milliliter is same as 1 centimeter cube of water. And what else are we given? We are given the temperature. Or before we do that, let's convert this volume, because we are not given the mass of the water, but density rho is equal to mass over volume. You have to recall that from your SS1, that density is equal to mass of the body over volume of that body. The mass per unit volume is called density. And what is the density of water? Density of water is 1 gram per centimeter cube. And mass of water, which we don't know here, all over volume of water, 250 centimeter cube. If you cross multiply, you will notice that your mass, or you get that your mass is equal to what? 1 gram per centimeter cube times 250 centimeter cube. This cancel this, and you have your what? Mass to be equal to 250 gram or 0.25 kilogram. That is, if you divide this by 1,000, if you divide 250 divided by 1,000, you have this in kilogram mass of water. And we are given the temperature of water. T of water, define the initial temperature of water. The initial temperature of water was given to be 20, and this water was heat, and the temperature raised to 35 degrees Celsius. That is T final. The final temperature is 35 degrees Celsius. We have to find the heat required. One thing is missing here, which is the specific heat capacity of water. If you check the slide, you also discover that the specific heat capacity is given there on that table. That is table 1.1. That C for water is 4,200 joule per kilogram per Kelvin. That is the specific heat capacity of water. And therefore, we can now recall that heat required, H is equal to product of mass, specific capacity, and change in temperature. That is mass C into bracket T final minus T initial, change in temperature. Our mass is 250 over 1,000, which is 0.25, times our C, that specific capacity of water, is 4,200, times our change in temperature, that is T final, 35 minus 20, and that will be 0.25 times 4,200 times 35 minus 20 will give us 15. If you multiply everything here together, we have 15,750 joule. That is 5.750 or 75 kilojoule. 15.75 kilojoule of heat is required to do that. That is 15.75 kilojoule of heat is required to raise the temperature of water from 20 degrees Celsius to 35 degrees Celsius if the water is 250 milliliter. Now let's go to question B. Question B. How much heat does 25 degrees Celsius of aluminium give off as it cools from 100 degrees Celsius to 20 degrees Celsius? Here we are given the mass of aluminium to be 25 gram approximately, or divide by 1000, you have 25 over 1000, and this goes to kilogram. This is aluminium, and if you also check your slide, you will see example 1.1 that the specific heat capacity of aluminium, C for aluminium, is equal to 900 joule per kilogram per Kelvin. Don't worry, whenever you find yourself in examination hall, they will always give you these values, like specific capacity of aluminium, of water, or every other material that will be mentioned there. So don't worry, don't disturb yourself. Now, again, we are given the temperature change, that is the initial temperature of aluminium was given to be 100 degrees Celsius, very hot, and this reduced to final temperature 20 degrees Celsius. And we can still apply, we also still apply our equation 1, that is heat required to do that, H is equal to MC change in temperature. And what is our M? Our M is going to be 25 over 1000 times our C, specific capacity of aluminium, 900, times change in temperature, that is T final minus T initial aluminium, and this will be 25 over 1000 times 900 times our T final is 20 minus 100. 20 minus 100. 20 minus 100. And this will be 25 over 1000 times 900 times minus 80. This cancel this, 0 cancel 0, 0 cancel 0. You are left with 25 times 9 times minus 8, which is going to be minus 1000, that is 1800 joule, or approximately equal to minus 1.8 kilojoule if you divide by 1000. The negative there, if you divide this one by 1000, to give you 1.8 kilojoule. The negative there implies that heat is lost. Example 1.2. As an illustration of a specific capacity determination, suppose a metal of mass 200 grams at 100 degrees Celsius is dropped into 80 grams of water at 15 degrees Celsius contained in a copper calorimeter of mass 120 grams. If the final temperature reached is 36 degrees Celsius, determine the specific heat capacity of the metal. Now let's see what happened. Let's analyze what happened here. We have a copper calorimeter, and we have water inside this copper calorimeter. This is water, and we are given the mass of the water. Let's see. We are given the mass of the water. That is MW, to be, mass of the water was given to be 80 grams. And also we are given the mass of the metal. We dropped a metal which was 100 degrees Celsius hot. This is the metal. The mass of the metal, and metal, 200 grams. We can do well to convert this into kilogram. That is, this will give us 0.08 kg. Divided by 1000, this will be 0.2 kg, kilogram. And we're given the mass of the calorimeter, the mass of the copper calorimeter. Let's call that M calorimeter. was given to be 120 gram, 120 gram, or which is 0.12 kilogram if you divide by 1000. Now, this metal was initially heated to 100 degrees Celsius. Was initially 100 degrees Celsius hot. That's the temperature. The initial temperature of the metal, initial temperature of that metal, that is T metal, is given to be 100 degrees Celsius. And the initial temperature of both water, that is water, and the calorimeter, that is plus calorimeter, the two of them together, they were initially, since the water was initially inside the calorimeter, then it means that they maintain the same temperature. And this was given to be, that is T, let's call it T initial for both of them, was given to be, we're given that temperature to be 15 degrees Celsius. And let's analyze that. We can notice that this metal was initially hot, 100 degrees Celsius, very hot, than the temperature of water and the calorimeter. Now, when this metal was dropped into this, then this metal begin to lose heat, begin to lose that temperature. The temperature begin to reduce. While the temperature of water begin to go up. That is, we can see that metal begin to lose heat for this metal, for this water and calorimeter, while water and calorimeter begin to gain that heat. Now, this will continue until equilibrium will be reached. That is, the two of them, the thermal equilibrium will be reached, which means that both the metal, the water, and calorimeter maintain the same temperature. And that temperature is the temperature, the final temperature of the mixture. They said the final temperature of the mixture is, that is final temperature of mixture, which is T final, or let's call it T2. We have 36 degrees Celsius. T2 is less than, that is the final temperature of the mixture, is less than that of the metal, the initial temperature of the metal, that is 100. And we can recall our calorimetry law, recall the calorimetry law, that heat lost by metal will be equal to heat gain by water plus heat gain by calorimeter. Heat gain by calorimeter. That is, we say heat lost by metal equals heat gain by water plus heat gain by calorimeter. So let's substitute that. Heat lost by metal will be given as mass of the metal, specific capacity of the metal, and change in temperature of the metal equal to heat gain by water, mass of water, specific capacity of water, change in temperature of water, plus heat gain by calorimeter, mass of calorimeter, specific capacity of calorimeter, then change in temperature of calorimeter. Now, what we are saying is that the total heat lost must be equal to the total heat gain if the thermal equilibrium is reached. and provided there's no heat loss to the surroundings. That's why we always lab this calorimeter when doing such experiments to prevent heat loss to the surroundings. Now, what is the mass of the metal? Mass of the metal is 0.8. Mass of the metal is 0.8 times the specific capacity of the metal is what we are looking for. The specific capacity of the metal, we don't know. But we know the temperature of the metal, that is the change in temperature of the metal. The temperature of the metal changes from 100 degrees Celsius to 36 degrees Celsius, which means the change in temperature will be 100 minus 36. 100 minus 36. 100 minus 36. And this will also give us mass of water that we use 0.08 times specific capacity of water. Remember that specific capacity of water is 4,200 joule per kilogram per Kelvin, and the change in temperature of water, the temperature of water changes from 15 degrees Celsius to 36 degrees Celsius, and which is going to be 36 minus 15 degree plus mass of calorimeter. From the question they say it is a copper calorimeter, which means we'll be using the specific heat capacity of copper. Mass of the calorimeter was given to be 0.12 times the specific heat capacity of calorimeter, that is of copper. That's what we are going to be using. And if you check that slide, if you check the table on the slide, table 1.1, you will see that specific capacity of copper is 400 joule per kilogram per Kelvin into the change in temperature of copper was given to be 36 minus 15 degrees Celsius. And this will give us 0.8 times Cm, then times 64 equals 0.08 times 4,200 times 21 plus 0.12 times 400 times 21. It implies that if we divide both sides by 0.8 times 64, Cm will remain 0.08 times 4,200 plus, that is 4,200 plus 400, plus 0.12 times 400, everything into 21 is common to both. We have everything into 21, that is 400, that is 0.12 times 400 into 21, all over, we have 0.8 times 64, and this will finally give us 0.08 times 4,200 will give us, this will be 1, 2, and this 1, 2, 42 times 8 will give us 8 times 2, 6, 16, 8 times 4, 32, 32 plus 1, 3, 3, 6, 33, plus this will also become 12 times 4. 12 times 4 will give us 48 into brackets 21 all over 0.8 times 64, and this will finally give us 336. Let's do that. 336 plus 48. We have 8 plus 6, 14, 7, 8, and we have 384 all times 21 all over 0.8 times 64. And finally, you will have, if you cancel everything will give you 630 joule per kilogram per Kelvin, and that is specific capacity of the metal. Please, if you check well, you will notice that the mass of metal we substituted was not correct. It's supposed to be 0.2. The mass of metal that was given to us was 0.2. And that shows all the 0.8, you change it to 0.2. Please, I'm very sorry for that. It was a mistake. And the only thing is that the answer does not change. The answer does not change. Go. Now let's go to example 1.3. An electric heater rated 15 volts. 15 volts, 60 watts. Fitted to a metal block, supplies it to the block. This is the metal block, and an electric heater was fitted to this block. And the rate of this rate was given to be 15 volts, 60 watts. Fitted to a metal block, supplies it to the block of mass 1.5 kg and specific its capacity of 400 joule per kilogram per Kelvin. Calculate the temperature. That is, calculate the temperature rise in the block of the, if the current flow for 10 minutes. Let's write the parameters. We are given the voltage of this heater to be 15 volts and the power rating to be 60 watts. And it means that we can easily get the energy. It means that the electrical energy supplied can be found to be what? We can easily get that to be E is equal to power times time. Since power is equal to energy over time, we know that power is equal to energy or work done per unit time, and therefore the electrical energy here will be what? Power times time. And this energy is going to be supplied to this to this metal in form of heat energy, that is transformation of energy. And therefore, what is our E? Our E will be equal to the power given was 60 watts times the time. We're given the time to be 10 minutes. 10 minutes. But we have to convert this 10 minutes to seconds. That is 60 times 10 times. Since 60 minutes make 1 second, 60 seconds make 1 minute. Since 60 seconds make 1 minute, it means that 10 minutes simply mean 10 times 60 seconds. That is how we multiply by 60. This was given in minutes. We multiply by 60 to have it in seconds. And if we have this, that is the energy supplied. Or 60 times 60 will give us 3600. Then times 10 will give us 36,000 joule. This 36,000 joule was supplied to the metal block, and we can now use the formula. Since it is transformation of energy, the total energy supplied by the heater, energy supplied by heater is equal to heat energy gained by metal. That is law of conservation of energy. What is the energy supplied by the heater? We say it is 3600 joule. 36,000 joule is equal to, what is the heat energy gained by the metal? The heat energy gained by the metal is the mass of the metal, C of the metal, times change in temperature or temperature rises of the metal. That is temperature rise of the metal. We are looking for dt. It means that delta T is equal to 36,000 all over mass of the metal times C of the metal. And from the question, we can have change in temperature of the metal will be equal to 36,000 all over mass of the metal was given to be 1.5 times the specific capacity of the metal was given to be 400. And by the time you do this, zeros we cancel 0, 0 cancel 0, you are left with, this is going to be 30 times 2. 360 divided by 30, 360 over 30 times 2 will give us 60. And this will give us 30 times 2, 3 times 2 will give us 6. 3 times 2 will give us 6. This cancel this will give me 60 Kelvin or 60 degrees Celsius. With this, we have come to the end of today's lesson. Thank you.